Hi, I'm Alistair, I'm a games designer, and in this video I'd like to demonstrate how you can create a fake bomb prop like this one. So the first thing I need to make clear is that this is not a real explosive device. This is a puzzle designed to be used in an escape room or a similar game, and it's been styled to resemble at least what a Hollywood definition of what a bomb might look like. So we've got an LED countdown here, I've got some sticks of explosive, and I've got various coloured wires. And what players need to do is to cut the correct coloured wire in order to stop the countdown and defuse the bomb before it detonates. If players cut the incorrect wire, or if they don't cut a wire before the countdown runs out, then the bomb explodes and they lose. So the second thing I need to make clear is that this is not a real explosive device. But that actually generates some interesting game design problems, because as a designer we want players to make interesting choices in our games. And for a choice to be interesting, it has to have some kind of meaningful consequence for the player. Now, the consequence for successfully defusing the bomb by cutting the right wire, well, that's quite easy to convey. You've got a sense of kind of relief, of celebration that you've averted disaster and saved the day. And perhaps we can play some sort of jubilant fanfare music to signify that. But how do you convey the consequence of getting the incorrect wire and the bomb exploding? I could obviously have a little loudspeaker here and I could write the word boom on the LED display, but that doesn't really convey the peril and the gravity of the outcome for the player. We need something a bit more theatrical. And that's why I've got this row of lights behind me. These are DMX lighting, which I've used in previous projects to kind of set the atmosphere of an escape room. So for example, I've used them to convey a police siren. So maybe players get discovered by cops at the end of a game or something like that. I've used them for a lightning strike as well. So you can create all sorts of atmospheric effects and these are run by an Arduino, which you can see in the corner there, that it is sending DMX messages to trigger these kind of theatrical effects. And that's what we're going to do when the bomb explodes. So let me show you it in action. Here I've got my bomb prop, it's already counting down, and you can see I've got my 4 coloured wires, red, green, yellow and white. Now I know that the correct sequence that I have to cut these in is first yellow and then white. You can change that to anything you want. You can have all 4 wires in the correct order, or just a single wire has to be cut. That's all changeable in the code I'll show you later. And you can either physically cut them, so using a pair of wire cutters like this, that's obviously the most kind of immersive feeling of getting the satisfaction of cutting through a wire, but it's a little bit more difficult to reset. Instead, I've just used crocodile clips at the end here, so I'm going to pull off the wires that I want to disconnect from the bomb. So first of all, let me show you what happens when I get it wrong. So the red wire, for example, should not be cut in this case. But at the moment, I've just got that set to give a time penalty. So you'll see the countdown there is on 2:43. If I pull that red wire off, you'll see I've lost a minute of time on the countdown. If I were now to pull off the green wire as well, you'll see I'll lose another minute. Again, that's completely configurable. So if you want to have an instant detonation when one of those is pulled off, you could set that, or if you wanted to lose a certain amount of time with the first incorrect guess and more time with the second guess, you can do that as well. That's all in the code I'll show you later. I've now only got 10 seconds remaining, so I'll take off the yellow lead, which is the next correct one, but I won't have time to do the white in time. My bomb has detonated. I was unsuccessful on that occasion. So now let me just show you the other outcome. So first of all, I'm just going to reassemble my bomb by reconnecting these connectors. So like I say, I'm using crocodile clips just to make this reset process a bit quicker. If you wanted to go for the more authentic kind of actually physically cut the wire, I do have screw terminals across the top here, so you could just screw in a new length of wire. It would take slightly longer to reset, and also you'd obviously end up wasting some wire each time. So crocodile clips I think are fine for most cases. So I just reconnected those, and then I'll just reset the processor here. What you'll see is it just zeroes out first of all, then it starts again from a 10-minute countdown. So what I should have done is I should have connected first, what did I say, the yellow then the white cable. So if I take the yellow cable first of all, and I just show you that happening, so you'll see that one has not incurred a time penalty. And then if I take the white off now, you'll see the countdown freezes there on 9 minutes and 38 seconds. The bomb has been defused, and this can now trigger another event. So it could trigger the final door opening the room and players escaping, or it could lead on to something else depending on how you want to use this in your gameplay. Okay, so now I've shown you it in action, let me talk through some of the components in a little bit more detail. So the processor I'm using in this case is a Wemos D1 Mini. Now this is similar to an Arduino if you're familiar with the Arduino range of boards, except it uses an ESP8266 chip rather than one of the Atmel chips. Now the main advantage and the reason why I'm using it in this project is that it has Wi-Fi built into it, and it is via that Wi-Fi connection that I'm sending MQTT messages to a Node-RED server, and that's what's controlling the light and the sound effects. If I were running this on a Nano or an Uno, let's say, that would be fine if I wanted this to be a completely self-contained prop. But to make a portable prop that has that wireless interface, I find that the Wemos boards are really good. They're very cheap. They're just as cheap as an Arduino. There are, however, a few oddities that you need to get used to working with them. So they have fewer overall pins than an Arduino. They've got 8 digital pins and only 1 analog input pin. So on a Nano you'd have 13 digital pins and 8 analog pins, so it's substantially less. And also some of those pins themselves have got slightly weird behaviours. So the D8 pin, unlike all the others which have pull-up resistors, the D8 pin has a pull-down resistor. A bit strange. And certain pins like D3 and D4, if you use those, you can't have them connected to a ground during boot up, because if you do, the thing will fail to load. So the way that the actual circuitry works in this puzzle, so we've got 4 GPIO pins here. What these are doing, when they're connected to the bomb, this bomb basically has copper wires going through it, and these are all connected to ground. So when the wires are connected like this, all of these 4 input pins at the top here are going to read a low signal. That's how we know that they're connected, because they have a complete circuit all the way through to ground. When you cut them, or when you pull them out, that circuit is broken, and what happens instead is that the pull-up resistor on the board will pull that signal up to a high voltage level, and these will suddenly read high. And in the code, that's what we use to detect whether any of these wires have been cut or not. Now that's fine, but like I said, some of these input pins, the pin 3 and 4 on the Wemos Mini, you can't have them pulled low and get it to start up. So I had to be a little bit careful about selecting which pins are used for which function here. I'll show you the wiring diagram, but just be aware you can't simply replace all of your existing Arduino projects necessarily with one of these boards instead, without doing a little bit of rejigging of what goes where. The display here, this is a TM1637 display. They're very common. I've used these in lots of projects as well. And this is wired to 5 volt to ground and to a clock and a data line. Now there's nothing special about those pins at all, so for those ones I kind of used some of the pins that were actually a little bit more constrained, I guess. But the thing I wanted to be careful about those is because this is a puzzle that I'm encouraging players to actually cut wires or pull out wires, I wanted to be very clear that I only want them to be cutting these wires. These are the wires that are part of the game. I've got some more wires here that are used to power the LED, And I've also got a cable here, which is the power supply. I want to be very careful to make sure that players don't cut those. So basically the rule I've gone for here is that I've covered this in black insulating tape, and I've also got a black cable here as well, partly to to draw players' attention away from it. What I should have probably done is actually use black cabling here as well. These are actually normal cables just covered in tape. And then there would be very clear advice in the room, do not cut any black cables. The only 4 cables you need to consider cutting are these 4. And obviously players would actually need to find some kind of instructions in the room somewhere. They could be deliberately obtuse instructions. If you've ever played the game Don't Talk, no, Keep Talking and Nobody Explodes, that's a bomb defusal game that has very deliberately hard to follow instructions, so you could do something like that, but you need to be really clear with players that they are not to cut any of the black wires particularly. There's other ways you could protect that as well. If I was installing this in a permanent kind of prop, what you might want to do is actually put a glass or a perspex shield around all of the electronics here, so that these were the only wires that were actually exposed for players to be able to get to. So that's something you might want to consider as well. The other thing I want to mention before I get any further, I have to be honest and say I personally am not really a fan of bomb props. There's the issues I mentioned about having that meaningful consequence for one thing. Personally, I don't think they're actually a great theme to make a game about, but I don't want to be making moral choices for you, so I'm just giving you the information. I think there's ways you can make them more interesting though, rather than this being an arbitrary explosive device. As with all of the puzzles, I really encourage you to make it part of the story that you're trying to tell. So why can't this be some kind of high-tech electronic device instead? And rather than creating an explosion, let's say it's going to create some sort of high electromagnetic pulse, which is going to, I don't know, delete everyone's Fortnite saved games or whatever it is. Something that is, at least some players would still perceive to have peril associated with it, but isn't quite such a sort of a hard topic, and one that is, mindless endangering of human life. I'll be honest, I'm not really that into that, but I will just, I'll let you make that decision. And the other thing to mention is in terms of whereabouts in the narrative of an overall escape game this kind of puzzle would work. Again, going back to my first comment about the meaningful consequences, meaningful choices and the consequences of your actions, if right at the start of the game players were presented this and someone just comes along and cuts the wrong cables, well, what happens then? Is that game over straight away? Do you give them a second chance? So if I were to use this, I would personally recommend putting it in as the set piece finale to a room and actually gating access to it until players reach that point, so that they don't have the opportunity to kind of accidentally end their game early. So maybe this is only revealed in the very last segment of the game. So that's how I'd use it. So here's a fritzing project showing how the hardware is wired together. Here at the bottom of the screen we've got our bomb device itself, and then at the top of the screen we've got our server, which is running node red, and that is controlling our DMX lighting via this Arduino UNO. And obviously the bomb communicates with the server wirelessly via this wireless router here. So we'll start off by taking a look at the bomb itself in more detail. So normally I would always color code the wires which I'm using in diagrams like this and in real life. So normally I use red for positive 5 volts, black for ground, blue for data and yellow for clock. But as I have shown in real life, I've currently sort of grayed out all these wires here just to indicate that these are not the wires that players need to cut at all. But you can trace the lines here, so you'll find that I've got this 5 volt line here is going into VCC. I've got the ground line is going into ground, and then I've got data in here which is going to D3, and the clock line which is going to D2. So that is my TM1637 LED display. And then the wires that the players actually have to cut I'm using D1 from this side of the board up here, and then I'm using D5, D6 and D7 up here. So when I originally designed this, I had D8, D7, D65 all in a row on this line, and then I realised that D8 didn't have a pull-up resistor, so I would have to add extra hardware in order to detect whether the wire had been cut. So then I shifted them all this way a bit and used this D0 pin here, but I realised that that caused problems if the wire was connected when the board booted up. So on the third revision, I decided to use this D1 pin, and that's fine. This works just like a totally regular GPIO pin. It's got no additional sort of constraints on it. So that's the reason why I'm chosen that slightly crazy wiring. And you'll see that all these wires come around here. They are threaded through the middle of my explosive sticks. These are actually sections cut off a broom handle is what I'm using. You could use any kind of tubes that you happen to have. Fireworks tubes are very are good to use because obviously they are actually designed for containing explosive charges in the first place. Also, one thing to note is that, as you may have seen in the video demonstration, I was actually powering the device through the USB connector, and that was wired to the USB input on my PC. I was just using that for debugging and monitoring the connection. If you wanted the bomb to be completely portable, you'd obviously have a battery input instead. And what you could use is if you have a hollow stick here, as well as using 4 sticks to actually carry the signals, you could effectively have another stick which you placed 3 C batteries or D batteries, for example, in a row. That would give you 4.5 volts of power, which would be enough to supply the power here. So you could actually kind of double these up as battery containers as well if you wanted for the device, if you wanted to make it totally portable. So that's actually all the wiring on that side. And then if I just show you what's going on here. So this is my PC that's running Node-RED. You can run Node-RED on a Raspberry Pi, on a Linux computer, on a Windows computer. I'm using Windows, but you know, depending on your setup, you might prefer to use a different OS. That's absolutely fine. This is connected to the same network that my Wemos is connecting to. So that's going to enable the Wemos to publish MQTT messages to the broker that's running on this server, that Moscow broker, which is part of Node-RED. And then I'm using the USB cable to connect to the UNO here. So this is exactly the same way that you'd connect an UNO if you wanted to upload code to it, for example, using the Arduino IDE, or if you wanted to monitor the serial monitor connection, you know, to debug information about what's running with the code. So this is both going to provide power to the UNO through that connector, and also enable Node-RED to send messages through a node out serial node to the Arduino, and then the sketch that's running on the Arduino is going to translate the incoming messages received here. They're going to be sent in a kind of a custom JSON format into DMX signals that are going to be sent through this output here and to our selection of DMX lighting. So I'm using a Concept Kinetics DMX shield here. You can actually create your own custom DMX shield on the UNO as well. You just need to have one of these kind of 5-pin DIN connectors on the end. The exact way that you configure that interface will depend on the particular lights that you've chosen to use. So the lights which I've got here, and I'll put a link for them in the description, these lights have channel 1 is an overall intensity channel, and then channels 2, 3 and 4 are for the red, green and blue components. And because I want to use all 3 lights to just achieve exactly the same effect, they are all listening to channels 1, 2, 3 and 4. So the Arduino here only needs to send 4 channels of data. But if you wanted to control them separately, to have them follow different patterns like a chase sequence, or to respond to different events because they're positioned in different physical parts of the room, that's easy to do as well. You simply kind of provide an offset as to which channel set they're all listening to. So these lights always need 4 channels. They need that intensity in the RGB components, but they don't all have to be listening starting at channel 1 of your DMX universe. You could have this one listening to channels 10, 11, 12, 13, for example, and this one could be listening to, I don't know, 100, 101, 102, 103. You can configure that on the light itself. So here's the code which I've got running on the ESP8266. I nearly said running on the Arduino then, because I got so used to saying that. But as you can see, I'm still using the Arduino IDE. The difference is that if you go to the Tools menu and to the Board option here, you can see that you can select different types of actual target boards, and I'm targeting the Wemos D1 R2 and Mini. So if you haven't got that option available in your Arduino IDE, you can come to your boards manager here, and you can see you can actually include support for lots of different sorts of manufacturers' boards, not just Arduino official boards. And the two I use the most are the ESP8266 and the ESP32 boards here. And you can also use other IDEs as well. It's just that the Arduino IDE is the thing that most people sort of use to start with, and if you're comfortable with this IDE, then it's fine. You can carry on using this, but actually target other devices. So there's quite a lot here, and a lot of it is quite similar to stuff I've mentioned in previous projects. So what I want to do is go perhaps a little bit quicker than normal over some of the bits which I to avoid repeating myself too much. So we'll start with the includes at the top. Here's some external libraries we're going to make use of in this project. The first one is to include the library that will give us the ability to connect to the Wi-Fi. And there's 2 different libraries depending on the hardware you're using. Now, in my demonstration, I used an ESP8266. I've just spoken about targeting an ESP8266, but this code will work fine on an ESP32 as well. And if you are using an Arduino, a genuine Arduino, and have got a Wi-Fi shield on that, for example, this code will run on that as well. So you include the library corresponding to the target platform we've got. This is the one which I'm using on the ESP8266. If you're using an ESP32 or an Arduino, use this one instead, but otherwise they're identical. Either way, we also want to include this library called PubSub client. You can download that from this GitHub link or via the Manage Libraries option up here, and that will enable us to publish and subscribe to MQTT messages, which is how we're going to communicate with Node-RED. And finally, this is a local library, which is an adapted version of this library you can get from here. Sometimes people have asked me, got a bit confused about having duplicate versions of libraries, things like that. You'll see that some libraries I include with these little angled brackets, and some libraries I've included with speech marks like this. So the difference there is that these libraries up here, these are ones that you have stored in your Arduino libraries folder. So that normally means that you've installed them through the IDE itself. So you've gone to Manage Libraries and you've either selected a file from this list, or you have added a zip library instead. And it will search your libraries folder first for this file. If you have speech marks like this, however, this is going to search for a library that's local to this project. So if you've got a complex project and you've broken it apart into several different sections, you want to use this one. So in this case, I've actually made a modified version of this library. I've placed it in the SRC subfolder of this project library. So that's why that is a slightly different syntax to this one here. Okay, so that's the includes. Then we get onto the constants. So these are values which are not going to change over the duration of the project. First of all, I'm going to specify how many different wires there are involved in this project. I'm using 4 for this example, which I think is a reasonable amount to choose from. You can always add additional dummy wires anyway to kind of, to give the player more options that actually aren't connected to anything anyway. So I think 4 is the maximum number of actual active wires you probably want to do anything with. And this is an array of the pins that each of those 4 wires are connected to. Now, I mentioned this briefly earlier, but you do need to be a little bit careful about if you're using a D1 Mini or an ESP8266, you need to be slightly careful of using some of the pins, because although they're still called general purpose input-output pins or GPIOs, there are ones with particular special functions. So, and I forgot this myself. So originally this array said D8, D7, D6, D5. I'd forgotten that D8 doesn't have a pull-up, so I then changed that to D1 instead. Yeah, you can, if you use this, if you're using exactly the same setup as me, this will be fine. This line here, so this is going to be how much time we deduct from the countdown for every time an incorrect wire is cut, and it's in milliseconds. So at the moment we've got that's 1,000 milliseconds, so that's 1 second, and then we've got 60 of those. So this is going to take off 60 seconds or a minute every time a wire is incorrectly cut. If you wanted to have an instant detonation every time any wire is incorrect, you could basically set this value to be very high, higher than the starting value of the timer was, and if that's the case, then you'll be guaranteed it's going to explode the moment any wire is cut. Here we've got some details required for the MQTT messaging system. So I've got the SSID and the password of my Wi-Fi network, which I want to connect to. This is the IP address of my server, which is running Node-RED, and the port that Node-RED is running on. And finally, we just need to identify this device on the network. So in this example, I've only got a single device, which is this bomb prop. But if you were using this in an actual room and you've got multiple network devices, you would want to ensure that you assign them all a unique ID. And I tend to use just 3-digit IDs. You could use the first digit to indicate the room or the area of the game they're in. You could use the second digit to indicate maybe the type of controller they were, and then the third one is unique to each thing. But anything you want really, so long as it will help identify this device on the network. Then we go to the globals. So these are variables which are shared between all of the functions in the rest of the script. So we'll initialize our display and we'll specify the pins that that's going to use. So I'm using D2 and D3 up here. Obviously they need to be different from any of the pins that you're using up here for your actual wire connections. So I am using most of the digital pins in this project, but that's okay. We're going to keep track of the last known state of each of the wires that's connected to the output pins up here. So were they high or low last time we read them, were they connected or not? We'll create an instance of our Wi-Fi client that we're going to use to connect to the network, and then we'll also create an instance of the pub subclient. So this is our MQTT object, and we're going to create that. We'll call it PC. We'll connect it to the server and port that we defined up here, and we'll also get it to use the network client that we defined here. So this is about the Wi-Fi and the MQTT network, this bit here. And then we go to more of the game configuration again. So in this section here, we're going to specify the solution, basically. What is it that players actually need to cut to correctly defuse the bomb? And there's a couple of different ways I could have laid this out. And what I've chosen to do is I've done another array that matches the length of the number of wires. So if you only had 3 wires to cut, let's say, you'd only have 3 elements in this array. And the way I've done this is if there's a 0 in that position, that means that that wire should not be cut at all. If there is any other number above 0, it indicates the order in which the wires are meant to be cut. So let's say you actually want players to cut all the wires and they want to just cut them in order that they are wired into. So to do that, you would have your array listed like that. So it'd be 1, 2, 3, 4. Or if you only wanted them to cut the final wire, let's say, you could do that by having your array like that instead. So that's the sort of the format of how I've decided to express that solution state. Here we have a little counter. just to show which one of these we want to cut next. So this actually starts at 1. I know many counters in programming, you're used to having them start at 0, but remember that I said that 0 here means I don't want the wire to be cut at all. So the next wire that I want players to cut is the wire in this array that has the value 1, which is this one here. If we get that correct, this counter here will increase to 2, and then we know that the next wire we want them to cut will be this one here. So that's why this particular variable here starts at 1 rather than 0, because I'm using 0 to kind of indicate a special state of don't cut me at all. We'll keep track of the current state of the device as well. So I've got 4 states here. Some of them are obvious. So inactive, it's not even been primed. Active is that the countdown is currently ticking down and players need to do something. Defused is that the player has successfully cut the right wires and the bomb has been turned off. And exploded is obviously either that the countdown ran down or that the wrong wire was cut. Now there might be occasions when you want to split those two outcomes into 2 different states. So you might want to say, okay, well actually how did the game end? Did it end through the incorrect action of the player, or did it simply end because of a lack of action? And you could do that if you wanted. Likewise, maybe you don't need to differentiate between when the bomb's inactive and when it's been successfully defused. But this is how it works. It's a simple state machine, we call it, just to keep track of what state the puzzle is in at the moment. And when we first start off, we'll create a variable called state and we'll initialize it in the inactive state at the very beginning of the script. This is a variable that's going to keep track of the timestamp at which the device will explode, and this is going to be how long the game is going to last. So we'll use this variable at the beginning in order to calculate when that one will be. Okay, so next up I've got a set of functions which describe the different actions really that can happen with the bomb. I've got activate, deactivate and detonate. So in each case what they do, you can see they move the state of the device to correspond to whatever action has just happened. In the case of activating the bomb, we set it to be active, and then what we do is we set the detonation time to be the appropriate time in the future. So we start off with the current time, that's what millis will give us, and then we add on to that whatever the chosen game duration is, so 10 minutes in this case, multiply by 60 to give us in seconds, and then multiply by 1000 to give us in milliseconds. So that will give us the time in the future when the bomb is going to explode if it hasn't been deactivated in that time. And we'll just output something to the serial monitor. In the case of deactivation, well, there's not much to do. We just change the state and just log a message. And if the bomb detonates, well, again, we change the state in the serial message, but we also publish a message. So this is this MQTT message, which we're sending using the pub sub client. So that's why we've got PC here. And we're going to publish it in a topic called toHost. So that is the name of the topic that the server is going to be listening to messages that are sent to that topic. And if a message is received in that topic that has this payload attached to it, boom, that's what's going to trigger our sound and lighting effects. So the reason why I have moved these into these separate functions is because they might be called from different places in the code. So to have them separated out into separate functions like that just makes it easier for them to be reused. That's why. Okay, and we go to the setup function. So this is run when the code first runs. We'll start the serial monitor. We're using that to output some information. And this is something which I think I've used in some projects, but I should probably get more consistent at using it. So there's a couple of predefined variables you'll get in every Arduino script. In fact, everything that's gone through this particular compiler gets it. So file with double underscores either side like this. This will tell you the file name, in this case it's called cutthewires.ino, from which this thing was compiled, and date and time will tell you the time at which you last compiled it and uploaded it to the board. And this is really useful if you, like me, have lots of different kind of Arduinos and ESPs lying around, and sometimes you can't remember what code has been uploaded to which one. If you include this at the top of your code, what you can do is plug it in and read the serial monitor output, and it will tell you not only what program is running on it, but also what version it is, effectively, when that version was compiled and uploaded. So that's quite a useful little tip to have at the top of your code like that. Then we go on to setting up the Wi-Fi. So the ESP Wi-Fi can work both as an access point and also as a station mode, as a client. So it can both have other devices connect to it, and it can connect to other networks as well. So in this case, we want to act as a client and connect to an existing network. So we'll set that mode up. We'll begin our Wi-Fi connection with the credentials that we specified at the top, and then we will simply wait until we connect. When we have connected successfully, we'll print out the IP address that we were assigned as well. Again, that's not actually required, but it's very useful when you're, particularly with networking devices, when there are just a whole ton of things that can go wrong. It's really useful to be able to see this visual log of what all your devices are doing and what stage of setup they got to. We'll initialize the built-in LED pin because we'll be using that as a visual indicator of what's going on as well. We'll make that LED flash when certain events happen. We'll initialize all of the pins that we're using to verify whether the wire's been cut or not. And we'll also we'll update our last state array. So remember, we defined this in the globals section at the top up here. If I can find it, there it is. So this is going to keep track of what the last known state of each of those wires was, and we'll take a reading of that right at the start in setup. So assuming all of your wires are connected, that should read low in every case because they should be wired through to ground. As before, we'll set the destination time in the future, just as if we were reactivating it. And here, this is where we specify what's called the callback for the MQTT client. So this is normally, throughout most of this code, what we're doing is we're using the ESP8266 or the bomb prop to send messages to Node-RED, which is going to trigger the lighting effect. However, having set up that interface, we may as well also include the ability for it to receive messages from the Node-RED server. So again, I've done this in lots of other projects. If you're using if you're setting up an escape room that has multiple networked props, it makes sense to be able to remotely reset them, or to remotely be able to force them to be solved as well, or just to monitor their status. So even though the functionality in the video I showed you only has information going one way, which is for the bomb to tell Node-RED to do something, this section here allows the bomb to receive messages from Node-RED or any other MQTT server and actually get it to change its behavior based on the message received. So that's what this callback does. So the message received is in this section here. It's in the payload, but it comes in as a byte array. So what we'll do first is we'll convert it to a character array. We'll put a proper delimiter on the end of it. We'll print out what the message was received. And then I've just kind of put two examples here of the ways that you might want to write this kind of action in. So the first one is if a message is published in a topic that's called reset, then what we can do is we can reactivate the bomb just as we would do at the start of the game. Or alternatively, if a message is received and the payload of the message is solve, then we can deactivate the bomb. The reason why I've deliberately chosen the words reset and solve in this case rather than activate and deactivate or detonate or defuse or anything that's specific to this project is that these tend to be keywords which I use across all my props, and I think for the vast majority of escape room puzzles can be applied. This concept of resetting a prop or solving it pretty much are fundamental to any escape room tech prop. So I tend to keep those same keywords there. The actual behavior that does on the device is going to differ from prop to prop, but I'm using those two as my general keywords. Now the next bit here, now let's actually turn the LED display on, so our countdown display. First of all, we'll set a brightness value. I'm not using the full maximum brightness. I'm setting quite near the top, but there's a little bit of room to make it brighter, but that's fine. Now, this bit here, you briefly saw it in the video, but I didn't explain in much detail. So again, this is just a little visual indicator to help you know what's going on with the prop as you turn it on. So I've got the serial print line messages, which I've had up here, but bearing in mind we've got an LED display attached to this device, we may as well also use that to do some kind of basic debugging as well. So what I've done here, I've got an array of 4 elements that are going to light up different sections of the 4 digits on the LED display. And initially what they're going to do is it's just going to light up the segment A and the segment D of each character in the display. That's the top line and the bottom lines. The 2 horizontal lines are always going to be lit up in every case. And then what I'm going to do is I'm going to loop over all the wires, and I'm going to use this to indicate those wires which have been successfully detected as wired to the bomb on startup. So I'm going to loop over all the wires. I'm going to put some serial output as well. But in this section here, so this is a little bit complicated, so I'll just explain what's going on here. I'm going to take a reading of each of the pins. I've got the little exclamation point here, so that's going to negate that reading. So that's going to say if this is low, which means that the wires are connected to the bomb. So if the wires are connected to the bomb, what I'm going to do is I'm going to add in these sections to the display corresponding to that character. So this kind of works particularly well in my case because I've got a 4-digit display and I'm using 4 wires. This wouldn't work or would need to be adapted if you had more wires than that, for example. But what this is basically going to do, so this is going to fill in the vertical lines for each character. So at the end of all this, when the bomb starts up, what you're expecting to see if all the wires have been connected is essentially a load of zeros, because that is the horizontal lines at the top and bottom that you get from this, and then you also get the vertical lines filled in from this if they are recognized to be connected. If you only see the horizontal lines at the top and bottom when you start up, that shows that that wire is not properly connected when you first start the program up. So again, that's kind of fairly specific, well, it's very specific to this prop, but it's just another example of how you can use an LED device. If you've got one plugged into your device anyway, you may as well use it for some kind of status output messages when your code first boots up, because it saves you having to plug in a USB connection. And in this example here, I am now arming the bomb at the end of the setup function. So I am automatically calling activate here. But if you wanted to, you don't have to automatically have the bomb activated on startup. You could comment out this line and instead have it wait until it receives that reset message from a server. So you could have the device on and it would remain in an inactive state, which remember is how it started off at the beginning here. So the countdown wouldn't be doing anything, the display wouldn't be counting down anything until it receives that first reset message, and maybe that could be triggered by a previous action in the room, for example. But for this simple case, I'm just going to have it become active as soon as it receives power. So I've left that on at the end of setup. Okay, and then we get down to the loop function. So this is the main program loop. It's also the last kind of function in this code. So we're nearly there. The first thing we do is all this section here deals with the MQTT sending and receiving of messages. So first of all, we'll check whether we are already connected to the MQTT server. If we're not, what we'll do is we'll try to reconnect to it. So we'll send our device ID and we'll try to reconnect to the server. And when we get there, what we'll do is we shall subscribe to any messages that are published to a topic that we want to listen to. So again, I've done this before. I have all of my devices listening to a particular topic. In this case, it's going to be to device, and then the device ID, which in this case was 100 because we defined that right at the top of the code. So if I wanted to send that reset or that detonate, or the reset or the solve message, sorry, which I've got up here, the channel I would need to send them to would be to device /100, and that would be picked up by this message here. If for whatever reason we can't connect to the server, then we'll put an error message up instead, and then we'll try again 5 seconds later. And the loop function here, this actually will send any queued up messages. This will check for any incoming messages as well. So this is a kind of like a sub loop just related to MQTT that we place within our main program loop, and we just call that once on every iteration. And then we'll actually get onto the game logic. So you'll see why I said I wanted to keep the logic for the game itself quite simple, because up to now we've kind of been building up a framework, but we haven't actually gotten to the specific functionality of this game. So this is where we get to that. We'll loop over each of the wires. We will see what their current state is, and also compare them to what their state was in the previous time we measured them. So if they are now reading high, that means they're no longer connected through to ground. So that means that they've been cut. And if their last state was low, well, that means that they weren't cut last time we checked. So this is effectively this is a recently cut wire. We haven't acted on this wire being cut yet. So what we'll do is we'll send some serial output. We will flash that built-in LED as well, just as another indicator of what's going on. And we'll update our last state, because last time we knew about it, it was low, but now we know it's high, so we'll update that value. And then we say, okay, well, this wire's been cut. Was it the right wire to cut or not? So we'll compare the counter value, which is this I up here. We'll see whether that was the next wire which we wanted the players to cut. And remember, I described that at the top of the code up here. So that's this section here. This said the index number of the wires we wanted to cut. So this one was the first wire we wanted to cut. This one the second wire we wanted to cut. And this is the number that they're up to so far, basically. So that's what we're comparing in this section here. So if the wire that has been cut is equal to the wire that we next wanted to be cut, brilliant. We'll go on to the next wire in that case. Otherwise, if it was any other wire, this is where we need to subtract the time penalty. So whatever we define that value was at the top of the code, we take it away from the detonation time in the future. So we go through all of the wires, and this bit I sort of added in. This isn't really necessary for the functionality, I suppose, but I added in. So this deals with the case of reconnecting a wire that had previously been cut. Now, because of the nature of cutting a wire, from a game point of view, it doesn't really make much sense to allow players to reattach it again. You know, it's meant to be a very much a decisive moment when they choose to cut a wire. But if for whatever reason you wanted to allow them to to adapt this puzzle and to reconnect a wire that's been broken, that's what I added this section for, basically. So this is the reverse set of conditions from that which we had up here. Here it's where it's now reading high and it was low before. Here is where it's now reading low and it was high before. So that means it's been reconnected to the bomb in that case. So we go over all the wires. We action all the ones that we know have been cut. And now what we need to do is test whether all the wires that we wanted to be cut have indeed been cut. So that's what this loop does here. We once again go over all the wires. We compare them in one at a time, and we'll say, well, if they had a value in that wires to cut array that was different from 0, 0 were the ones that didn't want to be cut at all. So if they've got something that's different from 0, it means they were meant to be cut, at least at some point. And if their last state is low, well, that means that they haven't yet been cut. Therefore, not all the wires have been successfully cut. This is a slightly weird way you might think of kind of arranging the logic here, but actually this makes sense. Rather than saying have all the wires that are meant to be cut been cut, what we say is have any of the wires that are meant to be cut not been cut. So it's kind of like a negative way of phrasing the question, but it does mean that as soon as we come across one that hasn't been cut and was meant to be, we know that there's at least one more left to do. So that's kind of why we structure it that way around. It might look a bit confusing, but that's how that works. So we've got to this point here. We know whether all the wires have been cut, and we decide what to do with the current state of the puzzle. So if we're currently in an active state, and the time now exceeds the detonation time, and this is the detonation time that may have already been amended up here. So it might have been brought further forward in time because of the penalty applied. If we now exceed the detonation time, well, that's the time to call the detonate function. Else, if we get to this bit here, so the bomb is active still, but now all the wires have been cut, so this section up here was successful, then it's time to deactivate the bomb. So that's what this section here does. In any other case where the bomb is active, what we need to do is update the display. So we'll work out how much time is remaining by working out the difference between the detonation time in the future and the current time now. We'll divide that into 1,000 and then take a modulo to work out the seconds remaining and the minutes remaining, and then we will show those values on the display. All of these bits here only happen in this case that the bomb is active. If the bomb is has been exploded already, or if it has been defused, or if it's inactive at the moment, none of this applies. The only thing that will bring it out of that state is the fact that we're still calling this loop function on every turn, and that loop is still listening for the callback function that we set up here. So if one of these messages is received, that's what can bring the bomb out of that inactive state. So it can either, by calling the reset function there, that's when it will start the bomb and ticking again. All of this section here only gets called when the bomb's actually active. So here's my Node-RED flow. There's not too much to it. And starting off at the top, I've got a single isolated configuration node here. And that's what's starting up my MQTT service. So in previous projects, I've used Mosquito, which is another MQTT broker. That's excellent. That's free as well. It's open source. But Node-RED actually comes with its own built-in MQTT service, which is called Mosca. So that's what I'm setting up here. So you can see it's running on port 1883. That's the standard port for MQTT servers. So that's just every time Node-RED is running, you'll be able to connect to the server on which Node-RED is running and access the Mosca broker directly. It's not quite as fully featured as Mosquito, but for a lot of purposes, if you're running Node-RED anyway, it will be a perfectly good replacement to Mosquito. So then we've got two possible flow starts here. This one is when the server receives an incoming MQTT message. So we're listening to that Mosca MQTT service we just started, and if anything is published to the toHost topic, we start this flow here. What we then do is we go into this node and we'll have a look at the payload of the message that's come in to that toHost topic, and if the payload is equal to the string boom, which is what's being sent by our bomb prop, then we divert the flow to output 1. Well, that in this case means to carry on going down the line. So output 1 is this link here that goes to this chain of flow at the bottom. But there is another way you can get to that chain here, and that's from this link. So it's always a good idea, I find, in any prop, but particularly wireless props, I guess, because you're just introducing that one more element of possible failure, I suppose. So it's always a good idea to have a manual override button, and that's what I've got going in here. So this is going to be exposed in my Node-RED dashboard, and clicking on that button, so let me just show you that. So here I've got that button, and clicking on that button will trigger the same sequence of steps, exactly the same as if a message had been received from the prop. So from this point onwards, it's identical whether we hit the override button or whether the prop worked normally. And then we've got sort of two branches that come off here. This top one here, this is about controlling the lights, and the one at the bottom is about controlling the sounds. So we'll have a look at the lights first of all. So this is a function node, so I've got a little bit of sort of code in this node in JavaScript. And what this is doing is to create the flashing pattern that I want. Remember that I showed a couple of different effects. I had a lightning effect and a police siren effect in the past. So I'm no expert on knowing exactly how you'd expect a bomb to detonate in terms of light intensity, but I've got a series of intensities here that basically start off at maximum, that's 255, and they continue at maximum for a bit, and then they go to 0, which is kind of like a blackout afterwards. If you wanted to, you could have these values kind of ramp up and down again, or you could have, you know, a series of individual flashes, however you want. But basically this array here describes how the intensity of the light is going to vary over this sequence that represents the lighting pattern of the bomb exploding. So then we loop over that array, and for each element in it, we set channel 1 of our DMX message to whatever the next element was. So starting at the beginning of the array, so we'll set it to 255, 255, 255. We do that so many times, and then we set it to 0 so many times. I mean, in a sense, I really don't need the array to be that long, but I've left it that long so that you can introduce, you know, some variation halfway along if you wanted to. Now, this section here, so setting the DMX channels, this is something that is going to vary depending on exactly what DMX lights you're using. So my DMX lights, and I'll put a link for them, have a number of channels. The first channel is the overall intensity, and then channels 2, 3 and 4 are the red, green and blue values. So for this particular effect, I'm setting RGB all to max, but you know, if you wanted to give it, I don't know, a blue sort of hint, a blue tinge to the light or something, you could decrease 2 and 3 slightly and leave this at max, and that would make it more blue. But I'm leaving them all the same, and I'm only adjusting channel 1, which is the lightning intensity. DMX doesn't prescribe, you know, what the meaning of a given channel is. That's something that depends very much on the actual lighting devices that you have in your DMX universe. So that might be something you need to change. And we'll simply send the message, and at the end we return and we go on. So this is sending a sequence of these messages with varying intensities of light. And what does it do? Well, it sends them onto, in this case, my serial connection COM5, because that is the serial port that I've connected to my Arduino. That in turn is then going to be passing them on to my DMX array. So that's the lights. And then the sound, well, I've got a file node here. This is a filing node, and I've pointed it to the location of my sound effect file, so my MP3 or my WAV file, whatever. And I'm then going to pass that to an audio out node. Now, there's a little kind of trick to do here. So audio out is located in the dashboard section of Node-RED. So what that means is this will play out of any device that actually has the dashboard loaded up. So this is the same dashboard where I've placed the button here, And in fact, if I show you this button again, you'll see that the group I've placed this in is called the sound and light group of the lighting panel. And I've put my audio out pointing to the same group. So what this means is that that file there, when the explosion is triggered, the audio will be played out of any device that is loaded to the dashboard page. Now in my case, I want that to be the the main Games Master computer, and what I'll do is I'll take a speaker output from that into the room. But you could have that being a device in the room itself. You could have that being a Raspberry Pi, for example, that was on this page, and what would happen then is that this audio out node here would play the audio in any device that was on this page on the network, on multiple devices in fact. So that's just something to bear in mind in terms of where you want the audio out to be sent to. And this is the code that's running on the Arduino UNO that's connected to the server that's running Node-RED via a USB serial connection. And Node-RED is going to write that set of intensity values via the serial output node, and this script is going to read those values over the serial connection and convert them into a DMX signal instead. So I'm using a modified version of the library that Paul Stoffrigan wrote here called DMX Simple, but again because it's a local copy, so I put it in speech marks here. And this is a very useful library. This is the Arduino JSON library. So JSON is a data format that is used for sending messages to all sorts of devices. It's nice and compact and easy to read. It's human readable, but can encode all sorts of data as well. So in this case, where I'm sending an array of values of variable length between devices, it's a really good way of sending it. So I'm using that library here. And that's going to help us sort of send this structured data from Node-RED to this device that represents all these different changes in lighting intensity. I've got two constants. These are defined based on the DMX shield I'm using. So I'm using this shield, which I've got a link to up here. There are other DMX shields available. You can actually make your own. It doesn't have very many components at all. It's mainly this Max 485 chip is what you want. But these are 2 pins on the Arduino that the shield kind of plugs into and are used for setting certain features on the shield. So those are hard-coded here. In the setup, we'll begin the serial connection. This is the serial connection. Normally we use a serial connection for debugging purposes and sending output messages to the serial monitor. But here, this is absolutely crucial to the function of the code because it's actually this same serial connection that we're going to receive messages from Node-RED from. And then we'll output some information as well. So this just explains the structure of the message we expect to receive. So you could type this message into the serial monitor if you wanted to. If you were running the Arduino serial monitor here, you could run this and just type this in and send it, and it would set the value of the lights. But we're going to be sending a message in this structure from Node-RED instead. This is where we make use of those 2 pins that I described at the top. So we set it to the correct mode, and we'll also specify what pin we're going to be using for transmitting the DMX messages to. And we'll just say what's the maximum number of devices that are sent. So basically when we send out our DMX, sorry, not devices, channels. So DMX has this concept of channels, and that's not the same as devices at all. So channel 1 might be a global intensity, for example, that many different devices can pick up that channel. 2, 3, and 4 in my case were red, green, and blue values, and then you might have other channels that have strobe effects and timings and all sorts of things like that. So this is a bit like saying this is the maximum size of the array that will be sent, and 512 is the maximum for DMX. So I'm gonna set it up to the maximum value, even though we're not really using all those channels. Some devices don't like receiving kind of incomplete DMX messages. They actually expect it to have a full 512 bytes of data in it, so we'll set the maximum there. And then in the loop, this is pretty straightforward really. So we'll check if there is any data that has been received on the serial connection. So this is like saying, has node red sent anything to that serial out node that is telling us to do something with the lights? If it is, then what we'll do is we'll create a dynamic JSON document, and we will attempt to deserialize the JSON string that was received. So this thing that kind of looks like this with a channels value and then square brackets and then various elements within that structure. We'll deserialize that into this doc variable here that we've just created. If we had any problems doing that, we'll just write some error debug. Otherwise, what we'll do is that when we'll create an array of all the channels, we'll loop over all of the values within that array, and we will sort of pass out the contents. So the channel, that's going to be an int variable, and the value is going to be an int variable, and we will pass them to the write method of the DMX simple library. So we'll say write this value, which we passed out of the JSON signature, to this channel, and we'll simply do that for all of the contents of the message. So it's just a load of pairs of values of channels and values, and we will write them all to the DMX simple library here, and that will take care of actually writing the hardware signal that's going to go out to our lighting effects or to our smoke generators or you know, anything else, other stage effects that are created, managed by DMX. So that's my take on the classic Defuse the bomb prop. The actual puzzle itself, as you probably worked out, is not very complicated. It's literally just a matter of following whatever instructions you've given the players to allow them to deduce what colour wire to cut. But hopefully I've been able to use this as an opportunity to demonstrate the ESP8266 wireless communication using MQTT to node red. That in turn is controlling a DMX signal on an Arduino that's then triggering theatrical sound and lighting. So I wanted to keep the puzzle quite straightforward to kind of fit in all that other complexity that's going on. If you wanted to make a more complex version of the bomb itself, maybe you'd want to have you know, a keypad unit or some toggle switches that had to be set to the correct position, or some other kind of more modular kind of inputs. Perhaps that's a project I can do in the future. If you'd like to see something like that, do please let me know in the comments below. This channel, I just do projects similar to this, so games and other device and components that are useful for an escape room or other similar contexts. So do please like and subscribe if you'd like to see more content like this in the future. As always, I will put up the code listings and the wiring diagrams to download and all that kind of stuff I will put over on my Patreon account. These videos are only possible because of the support of my amazing patrons, so thank you all so much. If you do want to check out the resources for this project and every other escape room project I've made, they're all over there, so do, if you are able to, and if you'd like to go over and see what else I've been up to and to support me there, that would be amazing. If not, I will continue to put these projects up here anyway, and you are free to just go and copy down the code and copy this and implement this in your own way. If you do so, please let me know. I always love to hear what people are doing out there with kind of projects based on these ideas. I think it's amazing. So yeah, thanks for watching. Let me know if you'd like to see, like I say, more complex modular type bomb devices in the future. And I will look forward to seeing you next month with a new project. Okay, cheers, bye.